We're trying to find a test for prime numbers, a test that we could apply to even really large numbers to tell whether it's prime. And we've already determined that when numbers are really big, the obvious approach of trial division is just not feasible. So is there some other way we can tell if a number is prime? Do prime numbers have some other property that distinguishes them from the composite numbers, besides just the definition of their factors are only one in itself? And so we're going to look at a property of prime numbers in this video that is interesting and not at all obvious. So I want to show this to you in an example. So let's take the number 5. Now we know 5 is a prime number. Now what I'm going to do is I'm going to take all the numbers from 2 up to 12 in this case, and I'm going to raise these numbers to the 5th power. Okay, and when you do that, you get this. Okay, fine. What I want us to pay attention to now is this column versus this column when we mod by 5, when we mod by the number that we raise these numbers to that power. So, for example, if I take 32 and mod it by 5, I'll get 2. Now, of course, 2 is also 2 mod 5. So we got the same answer here. A and a to the 5th were both the same when looked at mod 5. Look at the next one. 243, when I mod 5, I get 3. And of course 3 is also 3 mod 5. And we see this is happening again and again. And even on this one, 5 is of course 0 mod 5. 3125, also 0 mod 5. 5 goes into that evenly. Okay, and in fact, if I do all 12 of them, I get a perfect match. And in fact, you see that what's going on is it's going, we get the numbers just cycling 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. And the a to the 5th is also cycling 0, 1, 2, 3, 4. So that's interesting. So a and a to the 5th are equivalent. They are the same mod 5. Now, let's move to 6. Here are the numbers 2 through 12. Here they are now raised to the 6th power. Okay. Now if we look at these mod 6, what do we get? Well, 2 is 2 mod 6. 64 is 4 mod 6, right? We get 60 and then a remainder of 4. So in this case, they're not the same. 3 is 3 mod 6. 729 is, well, that one is 3 mod 6, isn't it? So those did match. Let's try the next one. 4 is 4 mod 6. 4096 is, well, 6 goes into 4092, I believe, so a remainder of 4. Okay, that one matched. 5 is 5 mod 6. 15,625 mod 6 is, it turns out it's 1, so that one did not match. Okay, so some are matching, some are not. And in fact, if we look at the finished table here, this one doesn't match, this one doesn't match, this one. Some of them are matching and some of them are not. So with 5 they all matched, with 6 they are not matching. If I do 7, again, here are the numbers 2 through 12 raised to the 7th. And now if I mod them by 7, 2 and 2, 3 and 3, 4 and 4, perfectly matching. So we got a perfect match with 7. All right. And in fact, I'm going to switch now to an Excel spreadsheet where I've worked this out for more numbers and we can just look at it a little bit quicker. Okay, so this one is for n equals 2. And again, the numbers, and I've gone up to 23 this time. Here are the numbers from 2 to 23. Here they are mod 2. Here are those numbers squared, and here they are mod 2. And you see the mod 2 columns are the same. So it worked for 2. We got a perfect match between a and a to the n in the mod n number system. With 3, it's a match again. When I mod both of them by 3, I get a match. 4, I do not. You can see, for example, this one isn't the same. This one isn't the same. They're not matching. 5, we already did. That one is a match. 6 is not. We saw that. 7 is a match. We saw that. And then moving forward, 8, not a match. Interestingly, if you take the numbers raised to the 8th power and mod them by 8, you always only get 0s and 1s. Not at all the case. Not matching this. 9, not matching. 10, not matching. Some of them do, but some of them don't. 11, they match. 12, not all matching. And 13, matching. So again, the ones that matched were 2, 3, 5, 7, 11, and 13. They are the prime numbers. So this is a remarkable fact, and it is captured in what is known as Fermat's little theorem. And Fermat's little theorem says that if you have a prime number p, so what I had been calling n, I'm going to call p because I want it to be assumed that it is prime now. If you have a prime number p, and then a is any natural number, a raised to the p and a are congruent mod p in the mod p number system. I've shown you a lot of numerical evidence that this is the case, and it can be proven, though I won't show the proof here. Okay, so this is a very important, very non-obvious fact about prime numbers. And this is going to be a really useful tool to test whether a number is prime. In fact, you can already see what we're going to say. We're going to say, if we want to test whether a number is prime, for example, to take an easy case, suppose we want to test whether 91 is prime. Now, obviously, we can figure that out without any fancy test, but let's use Fermat's little theorem to determine if 91 is prime. So what we could do is we could take any number, a, say 2, that's the smallest one we can take, and see what 2 to the 91 is, and see if it's congruent to 2 when we mod by 91. So we'll compute 2 to the 91 and mod it by 91 and see if it's 2. Okay, so let me switch to Wolfram Alpha so we can do a computation this big. So here's 2 to the 91. And so it's this very large number right here, 28 digits. And let's mod it by 91. So we'll divide by 91 and take the remainder, and we get 37. So we got 37, so no. It was congruent to 37 mod 91, not 2. It's not acting like a prime number should, according to Fermat's little theorem. So 91 has to be composite. So here we have a test that, if we fail the test, we know it's composite. Now, I want to be really clear. This is only a one-way test so far. It turns out that there are some composite numbers that pass this test. So if you fail the test, you have to be composite. But I'm not saying that if you pass the test, you have to be prime. There are some composite numbers that pass the test as well. So if you take 2 to the 341, it turns out that that is congruent to 2 mod 341. So 341 is acting like a prime number vis-a-vis the Fermat's little theorem. But unfortunately, it turns out that 341 is composite. It's 11 times 31. So it's kind of like a false positive that we got here. So this is not yet a perfect test. It will identify some composites, but it will not separate the primes cleanly from all the composites. And I'll have a little bit more to say about that in the next video.